said, we're doing some work on modeling the resilience of the Bay Area transport network. So the objectives of this work are, first of all, to build a model that can link individual bridge damage with the performance of the network as a whole over time. And then we would like to understand better how the performance of individual bridges within the network actually contributes to the resilience of the network as a whole, and how we can improve the resilience of the network by taking actions at individual bridges. Now for this work, we're using the Bay Area transport network as a test bed to sort of evaluate how feasible our techniques are. So to give you some idea of the network that we're using, we've got a picture here. We're describing the network as a graph of about 12,000 nodes and 33,000 edges, and we're including about 1,700 bridges in the network as well. Now this model was developed by some previous students, and we are working on refining and extending it for this work. The framework in which we're doing the network performance assessment is shown here. So the basic steps are to simulate ground motions. Now these are correlated and simulated at the sites of interest, in this case highway bridges. We can then sample fragility functions to get component damage at those bridges. And finally, we can compute the performance of the damaged network. And so all of this is repeated many, many times, simulated many times in a Monte Carlo framework. So the first piece of this work that we implemented was a recovery model. So this model was taken from Shinozuka and other authors from their 2003 paper, which models the repair of bridges after an earthquake really simply. And so basically the probability of a bridge being repaired by sometime t after an earthquake is modeled by a uniform distribution between some minimum time and some maximum time. So to give you an idea, for extensive or major damage to a bridge, that minimum time would be 80 days and the maximum time would be 300 days. And so this plot, I'm showing some sample, what we call recovery trajectories. So these have 10 time steps from 0 to 365 days, and they're for a variety of scenarios. On the y-axis, we have the fraction, of the network bridges that are functional. And so you can see we achieve, as you'd expect, full restoration by 300 days. Now at each time step of the recovery trajectory, we can also measure how the network is actually performing. So on this plot, for example, I'm showing the fraction of the trips that were able to be made on an undamaged network that can still be made in the damaged scenario. And we can also do similar things for travel time. So there are several next steps that we want to do for this work. The Shinozuka model is quite simple, and so we'd like to first of all check whether those parameters are still realistic. And we'd also like to add parameters to account for the fact that there might be delays because many, many bridges across the network might be damaged. There are likely impeding factors. And then also management agencies have recovery strategies, and so how can we model those accurately? We're also looking to testing other recovery models. And the second objective of this work is to evaluate individual mitigation actions and their effect upon the whole network. And so to do this, one approach we're taking is to model the system as a Markov decision process. So I just wanted to take some time to explain the basic setup of an MDP. So an MDP has three components. The first is the state of the system, and we can model this for this problem as a combination of the state of every single bridge in the network. So for example, a bridge might have a binary damage state and a binary retrofit state. Then as a manager of the network, you can take different actions at each of the bridges in a network. So you can repair them if they're damaged, you can retrofit them, or you can just leave them alone. And every combination of state and action results in some sort of reward. So that might be the cost of taking an action like repair or retrofit, or what we'd like to do is measure the reward as some function of the network performance, like the number of trips you can take or the downtime after an earthquake. Now when you solve an MDP, you are trying to find the optimal action to take at each step of the system to maximize the reward over time. And so we can do this easily and quickly for small systems like 3 bridges. I've shown some of the optimal actions to take for different states of a 3-bridge network here. But we would like to scale up to realistic size networks, and to do so, we're now working on training a reinforcement learning agent to identify the optimal actions for those larger networks. I'll now hand it over to Rodrigo to talk about another approach to evaluating mitigation actions.
In terms of the resilience of the transportation network, although we can look at actions on individual elements such as roads or bridges, it's more intuitive in terms of the decision-making process to look at whole sections of network, such as roads, highways, or bridges that are close together. Taking that into account, and by the advice given by Tom Chance, this team developed the concept of a corridor. A corridor within a transportation network is a series of links that are connected together and work jointly to deliver a specific service of the transportation network, such as connectivity, a section of the network that has a high capacity or has a high flow. Given a network, the way in which corridors are identified is by using a clustering process of taking the network as a graph. After having obtained all the corridors within the network, in order to decide what kind of actions we'll be taking in each corridor, we'll perform an optimization process in which the actions within an element of the corridor are going to be related to each other. In terms of the process that we have explored right now, we explored different clustering algorithms on different testing networks, and we decided that the best clustering algorithm was the Markov cluster algorithm, which is based on random walks. What does it mean? So for instance, if you look here, we have an example network, and the random walks consist, let's say that you're a user in node number 1. So if you're a user in node number 1, we would like to know what are the probabilities that you go either to node number 2 or node number 4. In this case, as you see, the numbers are pretty easy. The probability that the user will go from 1 to 2 is 6%. Then you'll calculate, given that the user is in 2, we'll go to 3, 5 will go back to 1. This is performed iteratively, and then the clusters of the whole network are going to be the section of the network that actually concentrates in most of these random walks that are more or less as a Markov process. So here is in terms of that network, here you see an adjacency matrix of the network, and then in order to get the probabilities of each node, you normalize by the row. And using this probability and two parameters are the inflation and expansion parameters, you can get the clusters in which in this case are two shown in that picture. We implemented the algorithm for the whole transportation network of the area, and here, although it's really small, but obviously I'm not waiting for you to. I don't expect you to look at the colors, but this is only to show you that we perform this analysis of clustering the whole transportation network, and we can zoom into the peninsula, and then we can zoom into the section of South San Francisco, and here you can see that the clustering process shows that there is a whole section of the network, in this case representing 101, that could be called as a corridor. So taking into account these results, our following steps is that we want to perform an optimization, both for the actions pre-event and for the actions post-event. There are different network performance parameters that we would like to explore. First, we would like to explore the cost of performing the retrofittings and the consequences, also the increase of commute time, and also we would like to include the recovery process that we talked before in order to quantify and minimize the downtime of the network. So as conclusions, first we have incorporated an initial recovery model into the network analysis so that time to restoration can be considered. Also, we're implementing the Markov decision process formulation to identify optimal mitigation actions with the goal of being applicable for large network with the problem that Gitanjali showed before. We also want to take into account network effects when evaluating decision, which means that we want to scale up the process. And finally, we are also exploring the use of network clustering to identify corridors and narrow the search for effective mitigation actions, trying to get the benefits of, instead of performing sporadic retrofit actions, trying to look at the benefits of using systematic actions of the network. And with that, do you have any question or?
Well, thank you very much. So, any questions from the audience?
I have one question. So, I don't claim I know much about MDP, but My knowledge is it is useful when you don't have a mathematical model. So you can use, it's a sort of unsupervised learning. Am I right in that sense?
So in the example I showed, I actually did use a mathematical model to quantify the state transition dynamics, so the probability of transitioning, for example, to a damaged state was a function of like the site hazard curve, so you can actually use it with those mathematical models.
And you doing that? Is that part of
Can
your
do
work? Incorporating some mathematical model
Yeah.
in the MDP?
So trying to leverage the peer formulation to find optimal options.
Interesting.
Any other questions?
I was just going to make the point on the recovery model that one of the challenges is that often after an earthquake, within 24 hours, maybe 48 hours, a pretty moderately damaged structure will just be shored up and kept in service, even though it would otherwise not be suitable for service. And so, so the model that says, you know, out to 80 days or something, and then you
Right.
start to go, that doesn't seem to really reflect, I think, reality for Caltrans.
And that's really helpful for us to know, because we sort of have thought 80 days seemed a little extreme. But
Yeah. I mean, it's sure that it's true repair isn't going to happen
Right.
that fast. I think that's probably what that Shinjuku curve is based on. But you know, after Loma Prieta, if you go around, you'd see structures all over the place that had shoring underneath them, and just that provided the level of insurance that allowed them to keep it open. So,
Thank
but
you.
but that's a hard thing to kind of put into
Yeah.
the model. So we can work on that later.
If I understood correctly, you're doing earthquake ground motion simulation and then modeling responsive individual bridges in the network. Can you comment on the level of detail of those models? I mean, that sort of sounds like an overwhelming problem to model a network with 1,500 bridges in it. I mean, how do you do it?
So what we do right now is it's a Monte Carlo analysis in which you have different scenarios. So for instance, this is only one realization that we showed before. So here in this slide, right? So here you have one scenario for motion intensity, like this rupture here in San Andreas. And then given the demand parameter, we use fragility functions for the bridges, which was with data provided by Caltrans. And then given the damaged transportation network, we compute different network performance measures such as commute time or connectivity.
So
So-
Caltrans has provided fragility functions at the bridge level
Yeah.
that represent the relationship between.
So we're not modeling bridges.
Got it.
Oh, yeah.
I didn't understand correctly.
No, and so that's a big step, and there's, you know, we're actually on another project where we're very active and going from what I think are some very crude fragility models to something that's more sophisticated, and we're hoping that we're going to get that in time to put those into your project.
We need that as well.
Awesome.
Great, thanks.
But I go back to my question again. So when you go to step 3, you calculate the network performance, but you have no way of telling if there is any error in your calculations, because you don't have. That's a form of unsupervised learning. You don't have labeled information. You don't have data that tells you that part of the network in this scenario didn't actually perform well, and then I predicted that. Is that right?
So, if I'm understanding your question correctly, so what I'm using as a measure of network performance right now is we have a traffic model developed by a previous student.
Right.
And so, you're right, I don't think that's calibrated to.
But
Natural
at the
state.
end of your 3 steps, you have assessment of the network performance. What I'm saying is there is nothing that closes the loop. There is no mathematical model that helps you to calculate the error
No.
in your assessment. So it's a form of unsupervised learning because you are not calculating error of
Yes.
your performance prediction.
Can I comment on that one though? But these are fragility curves, right? So these are based on the 50 percentile. So that takes into account at least some sort of error variability in your response. So if you're doing a mean model,
But that's in a
keep
bridge,
track of that.
bridge level, not on the network. So they cannot
right,
assess.
but they're doing
Yeah.
Monte Carlo simulations there that might, and I don't know enough about it, but
No, Monte
that-
Carlo simulation on the bridge level, but it doesn't tell you if the network performed this way they predicted compared to reality. Basically, there is no ground truth to compare to.
But
That's
it's
what I'm
hard
saying.
to compare a probabilistic-based model to a simple, I mean, if we have enough events, you can't just look at this one event. We
No,
can't just
it's
use
not the
one
event. If you have basically annotated information, if you have information that tells you in this scenario this network performed in this way, and I predicted this, and my error is 10%, and I should do that to bring the 10% to 2% or something.
But I don't know if you could do that when you're dealing with such highly probabilistic types of computations.
You may need more data.
We need more data, we need more earthquakes, is really what we need, and more buildings.
Or bridge damages.
Not in the Bay Area.
We had one more question, quick
Yeah,
question.
I was
finish off. Yeah.
just interested in your inputs actually. So the intensity measures that you're inputting into the model, where did those come from? Are you know, is there some uncertainty associated with them? And is that included in your Monte Carlo model as well?
So you're asking about the ground motion?
Yeah, the ground motions and whether or not they include, you know, liquefaction settlements and
Not
No,
liquefaction,
we're not
only
including
like
It's just shaking.
okay. So from I've done a number of projects with water distribution facilities, and it's the recovery time is really all based on where things liquefy. Maybe transportation facilities are a little bit different, but yeah, that's an important thing to consider in other networks at least.
Okay, well, thank you very much.